Now we go to another topic. In order to have a quantum gate, didn't we say that we need to have free rotation, right? Although we show Z and Y, but it can be other. We are going to have X and Y actually, usually. We don't use Z. Z, we just use the rotating frame, right? Or transformation. So now, but anyway, we need to show that we can go in other direction. Just processing is boring. If I can bring it down, then I can go to any places on the broad sphere. Then it means that I can implement any quantum gates. Because last time we showed that just use Euler rotation, right? About Z and then about Y and then about Z, I can implement any quantum gate, right? So our goal is to move it to other position, and this is related to an experience called rapid oscillation. So here has a lot of math now. So you don't need to be able to derive it, right? But I feel why I want to go through this, because if I just give you the answer, then might not be that meaningful, because I had a lot of difficulty when I studied to figure out all the math. Then why don't I just share you with all the math, and if you're interested, you go through the barrier, you can do more complicated thing. If you're not interested, you should at least see this one time. So that's why I want to do that. But in assignment, here I try to rotate about x-axis. In your assignment, you will need to rotate about y-axis. But basically, you just copy, change the sign. But I hope that you understand what's going on. Because this process helps us to learn many important concepts. One is the spin angular momentum operator. One is the rotating frame. One is the rotating wave approximation that you are going to see where in many places in the superconducting qubit that how people treat the qubit. Okay, so in order to start with this, we need to learn something about spin angular momentum. Why I do that? Because do you remember we have the magnetic field, right? I told you that if the magnetic field is in the z direction, then I say the Hamiltonian is equal to negative mu dot b, which are just two vector. But however, this is not correct. This is not correct because this is under the assumption that you already have the magnetic field in one direction. What if I have it in different direction, right? So I'm going to erase it because this is going to confuse you when you study. I will show you in the next page. Let's just learn this first, okay? So I'm going to generalize the spin angular momentum. Generalize the spin angular momentum. And you need to trust me, this is true. Just take it. So the spin angular momentum is defined by h bar over 2 sigma vector. Do you remember what is this sigma vector? This is called Pauli vector. Remember? It is sigma equals to sigma x, sigma y, sigma c. Or if you want, you can sigma x, x hat plus sigma y, y hat plus sigma z, z hat. Do you remember this one? We have done that a few times, including in your assignment 1. Right? You did the inner product of n and sigma and Pauli vector. Right? So this is just a vector, but it's not in real 3D space. You use the real 3D space as the basis, but its coefficient are matrix, are the Pauli matrices. Okay? So this is the generalized spin angular momentum. If you remember, our original spin angular momentum was what? It's just a vector, right? But now we promote it to an operator. So this is a matrix, right? So trust me, right? This is given, right? It works. So if we try to spell out, this is h over 2 sigma x, x hat plus sigma y, y hat plus sigma c c hat. I basically just repeating what we have said. And then I will just go through the exercise. This is 0, 1, 1, 0 x hat, right? 0, negative I, 0, y hat. And then 1, 0, 0, negative 1, z hat. And if you add them together, you just match the elements, right? So this is just equal to c hat, x hat minus I, y hat, x hat plus I, y hat, negative c hat. Are you okay how I get this one? Because I just add the element together, right? The first element is 0 times x hat, 0 times y hat, plus 1 times z hat. Second element is 1 times x hat minus I times y hat, plus 0 times z hat. And then I get this one. So you see that the spin angular momentum operator is a matrix. This is given. This is given. Right? If you go to deeper theory, of course, you can prove it. But we can try to check if this makes sense. Just check. For example, what is the expected value of spin angular momentum? Of zero state. This one is, if you understand the question, you can do it, then you basically understand the topic of this class already, this chapter already, right? But I guess maybe you still, some of you still are confused. First of all, I'm saying the state, 0, okay? And for this state 0, what is the spin angular momentum? And expectation value means that maybe I have different value and then I take the average. But after all, what is the spin direction of 0 in the setup that we have? I mean, spin up or spin down? For 0. Huh? Spin up. In the setup that we have, 0 means spin up. Right? Then what is the expectation value of so if spin up, I should say, okay. If it's spin up, then what will be the angular momentum? It should be pointing up or down. It's spin up, right? So of course it's pointing up, right? That's the other definition, right? We have said that spin up, you have angular momentum pointing up. But do you remember what is the value of angular momentum? Look at this. The spin of electron is plus minus half. Their angular momentum is plus minus half h bar. So now what is the expectation value of the angular momentum of spin up of 0? H bar over 2. Right? Because this is given, right? Half h bar over 2, and it's spin up, so it's plus, right? So I expect h bar over 2, right? So go back to think about, right, should be h bar over 2. Go back to think about all this confusing thing. Now, assume we don't know that. Then what can we do? Find the expectation value. I put in 0 as 0, right? Because this is something called spin angular momentum operator. I expect I put the state there, it will give me the angular momentum value of my state, the FH value. But I only have one value because this is very clear. It's spin up. It's not a superposition of anything, right? It's h bar over 2. So let's do the computation. This equals to 0 is what? 1, 0, right? And then you go through this long math. H bar over 2 z hat, x hat minus I, y hat, x hat plus I, y hat, negative z hat, and then 1, 0, right? I won't go through or if we step, but look at this. This one multiply this one equal to Z, right? Because this one times 0. And then you further use this to multiply, you only have the top one that has effect. Right? Maybe I write it one more time just to make it clear. This equals to H bar over 2, 1, 0, and then you get to C hat, X hat, plus I, Y hat. Is this okay? How I come to here? It's just this matrix multiply this one, right? So you get only Z hat and X hat plus I, Y hat are left. Okay? And then I further do multiplication. What is this? H bar over 2 C hat. Right? Is this correct? Yeah. It even gives me the direction. It gives me the vector, not just the value. Right? So from here, maybe you go back to do an exercise. It's not in assignment, but do an exercise. Find out what is plus state, the expectation. So basically, it's saying that what is the expectation value, right? So if I ask you what is the spin angular momentum of this state, what do you guess if we're talking about this state? It basically saying it's pointing in the x direction. The spin is pointing in that direction. So it is equal to h bar over 2x hat. Okay. Try to prove that this equals to h bar over 2x hat. Okay, any questions? So if it's difficult, I hope you can try to understand, right? If not, then this is the truth. Just take it for granted. In order to find, the spin angular momentum operator is what we need. It's not the vector, right? It's the operator. So as a result, you remember that earlier I tell you this is just the vector, but that is incomplete. We say the Hamiltonian is the magnetic field times the magnetic moment, right, in the product. And magnetic moment is the gyromagnetic ratio times the angular momentum vector, the vector of angular momentum. But in reality, it should be the magnetic field dot product gamma with the matrix, the operator, the spin magnetic moment operator. This one gives me a scalar energy. And this one gives me a matrix. And this is the right way if you have magnetic field going everywhere. Okay? Your question?
Is B in that case, is that like a Pauli matrix, or is it?
Still a vector. Magnetic field is still a real 3D vector.
So that vector dotted with the operator is you and one operator?
Say again?
That
Yes, because look at what is S again. S is a Pauli vector.
Oh.
Right? So 3D vector dot. This is just like the N in your assignment, right? N dot Pauli vector. Good question. Yeah. So you can look at this and think about it. You will understand better, right? But again, no worry. We are going to have the numerical example. So now we have a new system. Rapid oscillation. Besides having a magnetic field pointing down, I also have an oscillating small magnetic field in the x direction, external. Okay? And that is the so-called, the setup for rapid oscillation, right? So it is very straightforward. First, the setup, right? We have pointing down is negative B Z hat, right? And then you add this to an oscillating field, which is B1 cosine omega 1t x hat. That's it. You just say this is a vector along the x direction, but it's sinusoidal, so it's getting large and small and point in different opposite direction. Sinusoidal, right? So what is the total magnetic field? Now it's easy. I just add them together. It's just B1 cosine omega 1t x hat plus negative B0 c hat. Right? And of course, I can further write this as a vector if you really want. Then it is B1 cosine omega 1t negative B0 and 0 because I don't have any component in the y direction. Right? So you need to get used to this notation, right? This vector. So this one I set up the total B, and just like what you just asked me, what is this B? This is the B in this case. A vector, real 3D vector. Okay. Then what will we do after that? We set up what? The Hamiltonian, right? Set up the Hamiltonian, then I will be able to solve the Schrödinger equation. So I say, okay, the Hamiltonian is what? I just showed you in the previous figure. H equals to previous slide, negative gamma B dot spin magnetic moment operator. Okay, so I will just spell out negative gamma. We already say we know what it is. Then it becomes plus. Then negative gamma. Why I put a negative gamma? So this becomes positive, okay? So my cheat sheet has problem. So remember, gamma is negative because it's electron. The gyromagnetic ratio is negative, right? So we can see that I still keep negative. Then the gyromagnetic ratio is G E over 2M, right? Remember? Do I do something wrong? Negative B gamma. Ge over 2L. Yes. Yeah. So my cheat sheet is incorrect. Now, for B, right? What is B? B now I'm trying to do a dot product. So it is B1 cosine omega 1t, 0, negative B0. And then the whole thing multiplied to x, sigma x, sigma y, sigma z. Now, because G, right, G is approximately equal to negative 0.002. So this one is approximately equal to E over M. I missed one very important thing. What is S again? Yeah, thank you. So I'm missing this h bar over 2, okay? So here I should put h bar over 2 because S is Pauli vector times h bar over 2. So sorry about that, right? Okay, so that's why I missed this. So here I would put h bar and then 2, right? And then I will put them together. What is this? This is B1 cosine omega 1t sigma x minus B0 sigma c. Is this okay? A little bit too much, right? So, but basically this is just a vector inner product. Now, if you look at this carefully, I have two terms. One is the sigma x term, and other is sigma c term. I basically can say this equal to h0 plus hi. Where h0 equals to negative b0 h bar e divided by 2m sigma c. And hi equals to b1 B1 H bar E over 2m sigma and then cosine omega 1t sigma x. So here I have two terms, right? This term minus this term. This term is negative B0 H bar E divided by 2m sigma C. Have you seen this before? Look at this. This is the Hamiltonian under, oh, maybe not this one. This one. Negative E H bar divided by 2m times B0 sigma C, right? Memorize it, E H bar divided by 2m B0 sigma C. E H bar divided by 2m B0 sigma C, negative. They are the same. Why we have this term? This is due to what? It's clear, right? I have two components here. This is due to what? Yeah, due to this vertical DC magnetic field. Right? If you don't have B0, this term will be gone. But I have another term. So this is Hamiltonian. This is total energy. The main energy comes from this DC term. But I also have one more term, which I call it the perturbation term. It is small. We are going to make B1 much smaller than B0, okay, for this exercise. So this is a perturbation. So it's just like what? You are on a roller coaster. You solve the Hamiltonian. You know how it moves. Now you add some bump or vibration on the roller coaster. And of course you can solve the problem. But there are some perturbation method in physics that you can just treat those vibrations maybe as perturbation. And here we already have the solution of the true roller coaster that we did last time. And indeed you see that this one will give you a lot more precession. Right? So, okay, maybe very messy, right? So let me say again, in Rabi oscillation, we have a large vertical magnetic field and then plus a small horizontal oscillating magnetic field. Right? This is not difficult to memorize, right? This is the setup. And yes, then I gave you all this one. As I said, I don't require you to memorize it. We will do it in assignment, but probably not exam, right? I'm not trying. If I exam, I'll give you a lot of hints. But you need to understand. So this is the Hamiltonian. The reason we can get it is because we use the spin magnetic operator. So if you do this, basically it's just a Pauli vector dot product with the magnetic field. Magnetic field dot Pauli vector. Then go through this math, you have two terms. One is due to this vertical magnetic field, and the other is due to this small oscillating magnetic field. And because it's small, right, the main solution comes from this vertical one. So it is mostly normal precession, right? And then it do something else, and that is the rapid oscillation caused by this interactive term. Right? So I can give you the solution right away. And here, from now on, is just to practice some skill. You need to do it in assignment, but I really don't want you to get scared, okay? But I hope you learn this skill because maybe those who have taken quantum mechanics have no problem, but it's not too difficult. So without this Hi, which is the perturbation term, right? Then it will just have normal precession, right? We know that the system, the eigenvalues are negative mu B0, right? Maybe let me do a table instead. We know that it has eigenvalue of negative mu B0 for eigenvector Which eigenvector is that? Which state has negative mu BB0? Which state has negative mu BB0? 0 or a spin up, right? So this is the eigenvector, right? Or a spin up. And it also have another eigenvalue, which is positive mu BB0, which is 1, that is spin down. Now, I did not derive it. Actually, also, if you go through the math, right, I did not derive yourself. Actually, if I call this E0, this E1, E0 is also equal to negative h bar omega L divided by 2. Omega L is the normal precession frequency. E1 equals to negative h bar omega L, positive h bar omega L divided by 2. This is omega L. This one, the normal frequency. Normal frequency equal to EB over M, right? Which is equal to this one. Okay? E over M, if you go through that, you will get that, right? And then you multiply by H bar divided by 2. Okay, so this is given, right? So basically, I know this system has an eigenvalue that is 0 and 1, and the corresponding eigenfrequency are negative omega L divided by 2 and positive h bar, negative h bar omega L divided by 2 and positive omega L divided by 2. Is this okay? What I'm trying to say, just before you put on the small oscillating field, this is what you have. You have 2 eigenvalue and 2 eigenvector. So, there's something called perturbation theory. Many of us have not learned it, right? Because we did not really take quantum mechanics. But now let's just accept it. And it is easy to agree with Hi interacting Hamiltonian. Maybe this is perturbating Hamiltonian, sorry, right? Much smaller than H0. Then we say the states, the new states, right? This is the new states due to with perturbation. So go back to the roller coaster example. So I was able to find out how the car will move with the roller coaster. That was the given E0. I get all the eigenvalue, all the equation of motion. But now I try to vibrate a little bit, a very tiny earthquake during the roller coaster. Very tiny. I don't need to solve everything from scratch. I treat this tiny vibration as perturbation, Hi. And theory tell me that the solution is going to be equal to C0 of t e to the power negative I E0 dy h bar times t plus state 1 plus C1 of t e to the power negative I E1 divided by h bar t 1. So basically what you say is that, you now have a perturbation. You have an additional delta of energy. Very complicated. But because it is small, your state is approximately still equal to the original basis state, the linear combination of the original basis state. The reason you have this basis state is because you have a pure DC field. These are the basis state of BC field. But now you add a perturbation. I tell you that the base, you still get the state as a linear combination of the basis. Which one? This one? Yeah, both supposed to be negative. Yeah. So, except that the coefficient, first, you will have you will just modify by this phase factor related to the eigenenergy. That is the first thing. Second thing, your C1 and C0, these two coefficients are time dependent, and also you need to recalculate. That is what it means in the perturbation theory. And we accept it, okay? Because you can imagine if the perturbation is infinitely small, then this one should just go to the original basis vector, right? So if the disturbance is not too much, the basis is still the same. Okay, so we accept this one, but as quantum physics, what we require is T0 square plus, C0 square plus C1 square needs to be 1 at all time, right? Because the sum of their magnitude square need to be 1, because they represent the probability. Is this okay? And particularly in this case, I can also say that this is C0T e to the power, because you see E0 is just equal to negative h bar omega L divided by 2, right? So this is negative 1 h bar, and then h bar will get cancelled. Omega L divided by 2t, 0 plus C1 of t e to the power negative I. So here it becomes positive, I'm sorry, because it's negative, right? And here is still positive over 2. Right. The reason this becomes positive, because it was negative E0, but E0 is negative h bar omega divided by 2. So this becomes positive. Okay, so this is we know that, hey, this is the state due to this oscillating magnetic field and DC field. So our goal in the whole process is to find C0t and C1t. Is this okay? Think about that. So this is the setting up of the problem. Any questions? The rest I will go really fast, just math, and you can read my book chapter. I will send you hopefully by this weekend. Yeah, I think I don't want to rush. So if you want to do the assignment now, you can do it by following the book, right? But I don't want to rush. So, but any question? I mean, these 2 pages are the most important. You know how to set up. The rest is just math and some skill. Any questions? I hope that I can get it by this weekend. Yeah. Is this clear? The setup, the most important is you know what you're doing. A DC magnetic field plus small oscillating magnetic field horizontally, and you have the original unperturbed Hamiltonian, and then use this perturbation theory. Okay, so you accept it. Now, I know that the wave function is in this form, right? And then the rest is just a lot of math. Okay, so let's solve the equation now. Here I show you that the wave function is going to be like this. That's what we get from the last slide. So what is our goal? Solve the Schrödinger equation. IH bar partial psi partial t equals to H0 plus HI psi, right? Are you okay with this formula? Because the total Hamiltonian, I say that is the unperturbed one and plus the additional one, the perturbing one, right? Perturbation, right? Yeah? So how do I solve it? Now we need to have some trick. The trick is to do inner product. So though this is very long, I really ask you not to copy. Okay? But unless you understand, then you copy. Otherwise, now I will just keep writing something that you don't know what I'm talking about. Let's look at the left-hand side. Left-hand side is what? I H bar. And then psi. What is psi? C0. So actually, I need to skip step. What I'm doing here is doing the time derivative of psi, right? It means I need to do time derivative of this guy. That's very long, but we can do it. First, C0 dot. C0 dot means partial 0, partial t, partial c, partial t. I do the differentiation on this term first. So first, I do differentiation on C0, because this is time dependent, right? Times e to the power I omega lt divided by 2, 0. Am I done? Well, I want to differentiate this term. Now I differentiate C0. What else do I need to do? This one? It is plus, because it was negative E0, but E0 was negative, yeah. So I want to differentiate this term. Am I correct? Is it complete? What else? Do another term, right? Because chain, what do you call? Not chain rule. It's not chain rule. What do you call? So anyway, you need to do. Then now you differentiate the second term. The second term is I omega L divided by 2 e to the power I omega LT divided by 2, 0. Right? Because you differentiate A times B is differentiate A times B plus A times differentiate derivative of B, right? That's how I get this first term. Is that okay? So I do the similar thing for the second term. So second term will be C1 dot, and then I copy the rest. And then I will differentiate the second term. Again, I will differentiate. I got negative I omega L divided by 2 e to the power negative I omega L divided by 2. And then the whole thing times 1, right? Okay? So I differentiate this term. So then what? I will do the same thing to the right-hand side before further operation. Right-hand side is what? Right-hand side is just equal to H0 plus HI times the whole thing. So I will just write out C0 e to the power I omega L divided by 2, 0 plus H0 plus HI times C1 e to the power negative I omega L divided by 2t. Oh, I missed the t here. 1. Right? I did not do anything. What I'm doing is that this one applies to psi, right? So I just copy psi and then do the distribution law. Is that okay? Why do I do this? Because now my goal is that I want to find the coefficient one by one. I want to find, let's say I first find C0. Okay? In order to find C0, what I'm going to do is apply the bra of 0 state to the left. I just know that it works, right? You need to have this experience. And then I want to stop here.